Okay, now recording. All right. We are very likely going to end early today. All right, so we are here. My goal was for have 15.4 and 15.5. I only have one more problem to do in 15.4, albeit it's long. Okay, and then we'll do 15.5. Okay, and that's it. I'll give you the quiz and then have a good spring break. We don't meet again until Tuesday, April the 6th. Okay, and let's go ahead and set this now. Let's plan on exam 4 being Thursday the 22nd, regardless of when I finish everything here. So if I finish, much earlier, that's okay. Let's set it as Thursday, April 22nd. So just like the previous exam, if I finish early and I just get started with chapter 16, then fine, I'll just go ahead with chapter 16. Okay, and yes, let's go ahead and set the last regular exam as aiming for Thursday the 13th. So we're hoping for exam 5 to be Thursday, May the 13th. So what's going to happen on Tuesday the 18th? Review, question and answers about anything. Then our final exam is on the 20th, and then we're done. Okay, so that is our tentative calendar for the rest of the exams. Okay, so these scheduled dates for sections might still change, but let's set Thursday the 22nd of April for exam 4, Thursday 5/13 for exam 5, and our final exam is Thursday, May the 20th, and then we're finished, okay? Okay, so again, if I finish this, which I should be able to, 15.5 is not that long a section, as you can see right here. Right, so 15.4, I'm going to go ahead and mark it off. I was going to show you one more, then I would have done 3 out of the 4. Then 15.5 is on surface area. I'll do several of these and then give you the quiz, and then that's about it. I may just talk a little bit about what's up ahead. So after the spring break, there's a lot of triple integrals, okay? So it's the same concept, but triple integrals can get really long, as you might guess. Double integrals are already pretty long. Triple integrals, you have a dx, dy, dz in some order. Actually, well, our favorite, quote unquote, is dz first and then dy, dx, but you can have any order for those. And those aren't the only ones. There's other variations also that we have. Okay. All right, so again, where we are on the original schedule, 15.4, 55 was here, but we're not a whole week ahead. I think I'm really just one day ahead because of the fact that I'm trying to push this back over here. Okay, so if I follow the rest of the schedule according to what it's here, I should finish section 9 on Thursday the 15th if I keep the rest of the schedule intact, but we'll see how it goes. Okay. All right, so let's pick up where we were. So we were doing some of those physics type problems. So page 1018, definitely put this in your cheat sheet. X bar is my, m sub y, the moment about the y-axis divided by m, which is 1 over the mass, double integral of x times rho dA. Y bar is m sub x over m, 1 over m, double integral of y, rho of xy dA. And the mass is just a double integral of rho dA. So you have 3 integrals to compute. The original rho, x times rho, y times rho. Then you just divide. X bar is m sub y divided by m, which is this thing divided by m. And y bar is m sub x, this thing divided by m. Okay. And you don't need any of the other stuff. We're not going to do moment of inertia or probability or any of that other stuff. Okay. All right, so I was going to show you 11, then I'm going to show you 3 out of the 4, which is already 75%. So, to do 75% on the homework is really not that big a deal, since sometimes I end up doing 75% already or more. All right, so 15.4, number 11, a lamina, and don't worry about exact definition of a lamina. It's metal or sheet or whatever. All right, so it's part of x squared plus y squared less than or equal to 1 in the first quadrant. Find the center of mass if the density at any point is proportional to its distance from the x-axis. Proportional to the distance from the x-axis means this. So here's my picture. So as a function, I have y equals radical 1 minus x squared. Okay. So proportional to a distance from the x-axis, if I take any point, the distance from the x-axis is the y-coordinate. So rho is equal to k times y. That's what I want over here. Okay. So distance from the x-axis, if I take any point to the x-axis, that's considered the y-coordinate, right? So we have this region, y equals radical 1 minus x squared. Okay. So for the mass, I'm doing a double integral over the region R of ky dA. Okay, now you can tell from this kind of region, it's very convenient to do it in polar coordinates. The quiz today will be on polar coordinates also. Okay, so remember dA can be dx dy or dy dx or r dr d theta. Okay, again, planning ahead for dv, little change in volume, you can have dz dy dx or dz dx dy or 4 other variations, right? And those aren't the only ones. Okay, looking ahead, we're also going to have something called cylindrical coordinates, and we'll also have spherical coordinates, section 7 and 8, if you want to look ahead for that. So there's a lot of ways you can have dv, a tiny change in volume. But you know, if you have a tiny little box, right, you have a little change in the x direction, dx, little change in the y direction, dy, and a little change in the z direction, dz, right? Represented by a tiny little, I'm not going to say a cube. A cube means they all have to be the same, just a box, okay? Dx, dy, dz. All right, so in polar coordinates, y is r sine theta, and then dA is either dy dx, our favorite, or dx dy, or r dr d theta. Okay, and from this picture, r is going from 0 to 1, theta is going from 0 to 90 degrees or pi over 2. Okay, you have to put it in radians. All these are radians. All right, so that's going to be r squared. Okay, so I have r squared sine theta dr d theta. Okay, so rather than rewriting it, you know, to even rewrite a double integral or even triple integral is quite a bear in itself. So we know it's r squared. So I'm going to go straight to r cubed over 3. Sine of theta is constant. R equals 0 to 1. Factor out the k. K is a constant. Plug in 0, you get 0. Plug in 1, you have 1/3. So k over 3. Bring it out. And I'm integrating sine of theta d theta. Okay, integral of the sine is negative cosine. So negative k over 3 cosine theta from 0 to pi over 2. Negative k over 3, plug in pi over 2, cosine of pi over 2 is 0, minus sine, cosine of 0 is 1, so k over 3. So that's the mass. All right, so 1 down and 2 to go. All right, so m sub x by definition is y times the original rho. Right, so m sub y, the moment about the x-axis. M sub, let's see, what am I doing? Yeah, m sub x. M sub x, no, this one over here. Multiply the original by y and integrate. So the original was ky, so I have ky times y, or ky squared. Everything else is the same. Factor out the k. Y is r sine theta. It's r sine theta squared, y squared, times r dr d theta. So that's going to be r squared times an r is r cubed, right? So I have sine squared r cubed dr d theta. Okay, so integrate r cubed. Sine squared of theta is constant as far as r is concerned. So leave alone the sine squared of theta. R to the 4th over 4 from 0 to 1. Plug in 1, you get 1/4. Plug in 0, you get 0. So I'm going to put k over 4. And yes, I messed up again. Sine squared theta. Okay, so k over 4, sine squared. Okay, and you might recall from Calc 2, to integrate sine squared theta, you change it to 1 minus cosine 2 theta over 2. Remember that identity? You can put that on your cheat sheet if you wish. Okay, there were formulas for sine squared of theta and cosine squared theta. So sine squared of theta is 1 minus cosine 2 theta over 2. Do you recall what cosine squared of theta was? It's almost the same thing. Cosine squared was 1 plus cosine 2 theta over 2. All right, so I took the 2 out with the 4, that's k over 8. Integrate theta, integral of negative cosine 2 theta is negative sine 2 theta times a half. Again, that's the opposite of what I would do with the chain rule if I were differentiating. If I would differentiate, when I got to this stage, I would multiply by 2, right? So since I'm integrating, I divide by 2 or multiply it by half. Okay, again, you really don't want to use substitution if you don't have to, because there's so many integrals all over the place. It's easy to get mixed up. Okay, when I plug in 0, I do get 0, 0, sine of 0, 0. Plug in pi over 2. 2 times pi over 2 is pi. That's also 0. And again, that happens a lot. You might recall when you did this. So I just put pi over 2 there. So I get k pi over 16. So that's my m sub x. 2 integrals down, 1 to go. So m sub y. Double integral of, this time multiply the original by x. So the original was ky multiplied by x. Okay, take out the k. X is r cosine theta. Y is r sine theta. And once again, dA is r dr d theta. All right, so I have r cubed, sine theta, cosine theta, dr d theta. Okay, so again, sine theta, cosine theta is constant as far as r is concerned. That's an r. So keep it as r. So r to the 4th over 4 from 0 to 1. Once again, it's 1/4, right? Plug in 0, you get 0. Plug in 1, it's 1/4. K over 4. Sine theta, cosine theta, d theta. Okay, so if I do a u substitution, right? U equals sine theta. Du is perfectly cosine theta, d theta, right? Which means I'm integrating u squared over 2 or sine squared over 2. Okay, so again, if you can avoid actually doing the u substitution, just do it. Okay, so I put that there as 8. Sine of pi over 2 is 1, square root is 1. Plug in 0, you get 0. So k over 8. And there we go. So x bar is m sub y divided by m. So that's k over 8 divided by the mass, which was k over 3. Okay, comes out to be 3/8. Right, k over 8 times 3 over k. K's cancel out, 3 over 8. And y bar is m sub x divided by m. So m sub x came out to be k pi over 16 divided by k over 3. Okay, which is k pi over 6 times 3 over k. K's cancel out, 3 pi over 16. Okay, so the ordered pair, that's the center of mass, is 3/8. That's a 16 there. 3 pi over 16. Okay, that's the center of this thing. So you have this thing, right? That has a variable density. The density is not constant everywhere. Where's the center of mass? This point, 3/8, 3 pi over 16. Okay. And there we go. I am finished with that section. Okay, so 15.4 is done. 15.5, I will start. And it's on surface area. (15.5), page 1026. Surface area. Right, let's take a look at this function. We start off with a rectangular region to make it easy, but it doesn't have to be a rectangular region. It could be a general region. It could be a circle. It could be a triangle. It could be some weird shape. Okay. Again, please notice the wide variety of integrals we now have compared to Calc 1 and 2. We're just integrating over an interval from A to B, right? Now it seems very ordinary considering we can integrate over any region in the XY plane, and very soon we can integrate over any three-dimensional surface. Like we can integrate over an ellipse if we want, or a sphere, or a cube, or a box, or anything that we feel like. All right, but right now let's consider surface area. Okay, so in this function, it's a function. This is on the floor. If you go straight up, it passes the vertical line test, right? So I have this sheet up here, and it goes straight up. I want to consider the surface area. What's the surface area of this thing? Okay, so here's a tiny little dA. Right now they call it delta A. In the limit, it's dA with a delta X and a delta Y. Okay, so how do I analyze surface area of this? Okay, so theory, this is theoretical. You don't have to take notes if you don't want to right now. I'm not holding responsible for it. Okay, but for very, very small delta X and delta Y, it's almost a plane, right? In fact, we can find the equation of the tangent plane to that surface, right? We know how to do that. Okay, so for dA, which has a very tiny dx and dy, again, what's the difference between dx and delta x? Dx is a real small, technically, delta x, and dy is a real small delta y. Okay, so if I make delta x and delta y real small, I almost get a parallelogram, right? See up here? It's not quite a parallelogram, but if I chop it, chop real finely, it looks more and more like a parallelogram. Okay, with vectors A and B, see the vectors A and B there? A is in the X direction, B is in the Y direction. I know how to find the area of that parallelogram, right? It's the magnitude of the cross product. We did that a long time ago. Okay, here are the components of A and B. So A's components are delta X, 0, and I don't know if you can see it there, Fx. Okay, it's the rate of change of Z with respect to X. And the components of Y, in the Y direction, there's no I component, there's a delta Y, and the partial derivative of Z with respect to Y, that's the net change in the Z direction. Okay, you can work out that cross product, comes out to be this. The magnitude of A cross B, this came out negative, this came out negative, but very fortunately you're squaring it anyway. So it ends up being Fx squared plus Fy squared plus 1 squared, which is 1. You can see that. Okay. And you do that for every single one of these. The idea in calculus is whatever works for one works for all. So if you chop this up into a whole bunch of rectangles, okay, same logic applies where the net change in surface area is that square root of Fx squared plus Fy squared plus 1 delta A. So in the limit, it becomes dA. Okay, so here we are. Bottom line, if you say I have absolutely no idea what you were talking about, it's okay. What do you need to do to get through the homework and the test, right? Equation 3. So put 3 on your cheat sheet. A of S means the surface area above some region in the XY plane. Okay, that region does not have to be rectangular. Okay, it can be a general region like that. Okay, but here's the formula. Okay, double integral over the region D, square root of Fx squared plus Fy squared plus 1 dA, either like that or like that, square root of 1 plus partial of Z with respect to X squared plus partial Z with respect to Y squared. To me, it's short of you should say Z sub X and Z sub Y. Here, I'll write it like this. Hope my book doesn't fall. Z sub X squared plus Z sub Y squared. 1 plus Z sub X squared plus Z sub Y squared dA. Okay, and they're noticing the higher dimensional analogy to arc length. In Calc 2, you had arc length, which was radical 1 plus dy dx squared. just add another dimension. 1 plus derivative with respect to x squared plus derivative with respect to y squared, dA. Okay, so it's very consistent. It's a higher dimensional analogy to finding the arc length, right? When you're finding the arc length in Calc 2, you did this. So for surface area, just add the next, there's a derivative with respect to x squared. Now here's a derivative with respect to y squared, dA. Okay. In a nutshell, use this to find surface area. Okay. That's it, folks. Okay. But keep in mind, dA, well, you have a choice. It's either dx dy or dy dx, or in polar coordinates, r dr d theta. Okay. There's actually not that many problems where the answers come out quote unquote nice. So that's the reason why, there aren't that many problems that we have here. Okay, but let's just go right to it. So what do we have on our homework? And I'll end up doing a bunch of them anyway. So just 1 through 9 and also 8. That's only what, 1, 3, 5, 7, 9, and 8. That's only 6 problems. So I'll do half, 3, or maybe 4, and that's it. Okay, so 9 is the biggest. So I'll show it to you for those of you who don't have the book and aren't getting it. Page 1028. Find the area of the surface. So 1, 3, 5, 7, 8. And where's 9? Yeah, there's 9. Okay, so we're talking about surface area now, right? Area of a surface. We can find the surface of this shape, the paraboloid, okay? Or something that looks like that, or whatever. All right, so here we go. Okay, number 1, they gave it to me as 5x plus 3y minus z plus 6 equals 0 on 1, 4 cross 2, 6. So notice they even use that language. See that number 1, 1, 4 cross 2, 6. It's not a cross product. It means x goes from 1 to 4, y goes from 2 to 6. If they have another cross, then that's for z. Okay. Yes, you could say, 1 less than or equal to x less than or equal to 4, 2 less than or equal to y less. After a while, it gets so tedious to write all this out. You don't want to have any shortcuts that you can. Okay, so you have a plane. Okay, so imagine you have your piece of paper and it's crooked, right? It's going at some angle. Okay, and it's over a rectangular region. What's the surface area? All right, so first I have to write it as solving for z. So move the z over 5x plus dy plus 6, right? All right, so I need the partial with respect to x, z sub x, that's easy, 5. Z sub y, that's easy, 3. So double integral, x goes from 1 to 4, y goes from 2 to 6 of radical 1 plus fx squared, 25, plus fy or zy squared, 9. This is radical 35. That's a constant. Take the radical 35 out, and you're doing the double integral of dA. The double integral of dA is just a, recall. Double integral dA gives you the area. Triple integral of dV is the volume. And I guess a single integral of dx is length of an interval. Okay. So I just take radical 35 times the area, length times width. So 3 times 4, 12 radical 35. That's all there is to it. Pretty easy, right? For that one, at least. Okay, so one more time, write it as a function. Okay, we're used to functions, y is a function of x. Now, for the most part, it's z is a function of x and y. So you have to solve for z. So I move the z over, and it looks like this. So find the partial with respect to x, 5, partial with respect to y, 3, then go double integral, radical 1 plus 5 squared plus 3 squared. Radical 35, that's a constant, bring it out. So it's a double integral of dA, which is just the area. 3 times 4, from 1 to 4 is 3, right? And from 2 to 6 is 4. So radical 12 radical 35. All right, number 3, 3x plus 2y plus z equals 6 in the first octant. That's all they say. Okay, first octant. Here we go. First solve for z. Z is 6 minus 3x minus 2y. Okay. So here's the picture. I'm basically trying to find the area of that triangle. That would be the surface area. It's not as easy as you might think, actually. All right, so first I need to figure out where it touches the x, y, and z axes. Okay, so x-axis means y and z are 0. Cover this up. 3x equals 6, x equals 2. 2, 0, 0, right? Y-axis means x and z are 0. 2y equals 6, y equals 3, 0, 3, 0. Z-axis means x and y are 0, z equals 6. So here are the x, y, and z intercepts. 2, 0, 0, 0, 3, 0, 0, 0, 6. Okay, now, I need to figure out the region in the xy plane that I'm integrating over. It's a triangular region, right? So see this region right over here? I have to think back to my regular xy. If you kind of turn it like this and move your head, you kind of see it. But in the regular xy plane, just ignore the z coordinate of 0. So that's 2, 0, and 0, 3, right? So this point here corresponds to that point. That point corresponds to that point. I know I got 2 pens. Why don't I just use both pens? So here's the origin. 2, 0, 0, 2, 0, 0, 3, 0, 0, 3 in the xy plane. We prefer type 1, meaning y goes from one function to another. Okay, so I have to figure out this function. Okay, the y-intercept is 3. The slope is 3 minus 0 divided by 0 minus 2, which is negative 3 halves. So this equation is y equals negative 3 halves x plus 3. Slope is negative 3 halves, right? Double check. If you plug in 0, do you get 3? Yes. And if you plug in 2, do you get 0? Yes. All right, so for the surface area, I'm integrating radical 1 plus z sub x squared plus z sub y squared. So z sub x is negative 3, derivative with respect to x. Z sub y is negative 2. So that's radical 1 plus negative 3 squared is 9, plus negative 2 squared is 4, dy dx. Okay, y is going from 0 to negative 3 halves x plus 3. And x is going from 0 to 2, as you can see here, right? Take out the radical 14, and you're integrating dy, or 1 dy. That's like this. So it's simply the length of the interval, so to speak. You see here I have length of the interval. It's just that minus nothing, which is that, negative 3 halves x plus 3. Okay, so again, using this concept, integral of 1 dx is just the length of the interval. Double integral of dA is a, triple integral of dv is v. Okay, looking for shortcuts, whenever you can use a shortcut, do it. Okay, so radical 14 comes out, integral of dy, or 1 dy. If you're not convinced of that, integral of 1 would be y. You would plug in that, then you plug in 0. So there it is, you have that. Okay, so last thing is just integrate that. That's the only thing that requires a little bit of work. So that's what? Negative 3 halves x squared over 2 plus 3x. From 0 to 2, plug in 0, you get 0. Plug in 2, let's see, you have 4 over 4. They cancel out, so it's negative 3 plus 6. final answer is 3 radical 14. Right, so 3 radical 14, that's the area of this triangle right there. Okay. Okay. 7. The part of the hyperbolic parabola z equals y squared minus x squared that lies between x squared plus y squared equals 1, x squared plus y squared equals 4. That sounds very much like I should switch over to polar coordinates, right? That's a circle center of the origin radius 1. That's a circle center of the origin radius 2. So if you can imagine, here's the function, x squared plus y squared equals 1. X plus y squared equals 4. I'm integrating over that region. It has some shape. I'm finding the surface area only above this shape. There's a hole in the middle. See the wide variety of objects that we can integrate over, which makes look like the stuff you did in Calc 1 so ordinary now, right? You integrate from A to B. Is that all? Right? We're integrating over, washers, as it were, stuff like this. Right, so this is tailor-made for polar coordinates. R is going from 1 to 2. Theta is going all the way around the circle, so from 0 to 2 pi. Okay. All right, so z sub x is negative 2x. Z sub y is 2y. So by formula, double integral over the region. What's the region? It's this washer. Okay, big circle, little circle, throughout the little circle, that region. So radical 1 plus z sub x squared, 4x squared, plus z sub y squared, 4y squared, dA. Okay, and one of the versions of dA is r dr d theta. So radical 1 plus 4 parentheses x squared plus y squared. And you know from polar coordinates that x squared plus y squared is r squared. So radical 1 plus 4r squared r dr d theta. Again, look for shortcuts. Shortcuts. Constant, 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 constant. This thing does not depend on theta. Take out the 2 pi. That's the length of the interval of theta. Okay, so 2 pi comes out. U substitution. U equals 1 plus 4r squared. The derivative is 8r dr, so put it 8 inside and 1/8 outside. Okay, so again, shortcut. 2 pi is the length of the interval of theta, so to speak. It's a constant. Okay, again, if you're not convinced of that, if you integrate with respect to theta first, this is all constant. So you put a theta, plug in 2 pi, you get 2 pi, plug in 0, you get 0, you got 2 pi. There it is. All right, so you're going to integrate radical u. U to the 1/2. So u, there's the u, to the 3/2 divided by 3/2 is times 2/3. Okay, a little bit of cancellation here. 2 cancels the 4, that's pi over 6. Okay, plug in 2. You have 4 times 4, 16 plus 1 is 17. 17 to the 3/2. Plug in 1. 1 plus 4 is 5. 5 to the 3/2. Okay, and that's sort of the answer, but I'm very particular on this. So the Melvin-Hom rules are you should never leave an answer to the 3/2 power. Write it like this. 17 to the 3/2 is 17 radical 17. 5 to the 3/2 is 5 radical 5. Okay, to justify that, when you raise it into 3/2, 17 is 17 to the 1, right? Radical 17 is 17 to the 1/2. I can write it. 17 to the 1, 17 to the 1/2. And then you can say, oh yeah, 17 to the 1.5 or 3/2. Okay, so raising something to the 3/2 should always be this way. Okay, so final answer, pi over 6, 17 radical 17 minus 5 radical 5. Okay, so x to the 3/2, x radical x. Okay. I don't know. 23 to the 3 halves, 23 radical 23. Write it like this. Okay, so there's that. I'm finished this paper, so let me show you this. I was going to do number 8, and now I'm finished, folks, maybe even before 7. So we won't bother breaking. I'll just go straight to the quiz. We're done, and then have a good break. Okay, so for focusing purposes, I'll aim this a little bit better. Want to look at the video later? There's that. Okay, in fact, problem number 7 is a good setup for the quiz that I'm about to show you. Okay, so I was just going to do number 8, and then we're finished. And I would have done what? 1, 2, 3, 4 out of 6. How's that? See, 1, 3, 5, 7, 9, and 8. I would have done 4 of them, 67%. So it's almost 70%. And there we go. Number 8. The surface of Z equals blah, 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 blah. X is going from 0 to 1. Y is going from 0 to 1. Okay, hopefully that's not too bad. So that's a square region. Above that square, imagine this square. Above it, there's some function. Okay, it's probably curved. What is the surface area just above that region? Okay, derivative with respect to x, 2/3 times that is x to the 1/2, or radical x. Derivative with respect to y, that's constant. So y to the 1/2, radical y. All right, so by formula, I have a double integral, 0 to 1, 0 to 1, radical 1 plus radical x squared, nice, x, plus radical y squared y, dy dx. Okay, but if you say that's going to be real easy, it actually isn't that nice. Okay, so integrate dy. So this is to the 1/2. So it's 1 plus x plus y to the 3/2 divided by 3/2, which means times 2/3, right? Y goes from 0 to 1. Okay, so if I plug in 1, I have 2 plus x to the 3/2. If I plug in 0, I have 1 plus x to the 3/2. So it's not as nice as all that. All right, then I integrate with respect to x. So 2 plus x to the 5/2 divided by 5/2 means times 2/5. 1 plus x to the 5/2 divided by 5/2 means times 2/5 from 0 to 1. Okay, 2/5, factor out the 2/5. I have 4/15 out in front. Is that okay? All right, they both have a 2/5. So 2/5 times 2/3, 4/15. Okay, plug in 1. I have 3 to the 5/2. Plug in 1 here. That's minus 2 to the 5/2. Okay, minus, plug in 0. 2 to the 5/2. Plug in 0 here. 1 to the 5/2, which is 1. Okay, so I just have to clean this up. 3 to the 5/2. These two are the same, right? Minus 2 to the 5/2 minus another 2 to the 5/2 minus a minus 1, so plus 1. So it's minus 2 times 2 to the 5/2. That's 2 to the 7/2. Okay, so I have 4/15. 3 to the 5/2 minus 2 to the 7/2. 2 times 2 to the 5/2, 2 to the 1 times 2 to the 5/2, 1 plus 5/2 is 7/2. Okay, how do I make it like a nice radical? 3 to the 5/2 is 3 squared times 3 to the 1/2, right? It's 2.5, 2 plus a half, 5 halves. And 2 to the 7 halves is 3.5. So 2 to the third, 2 to the half. Okay, so best final answer, 3 squared is 9, radical 3, minus 2 cubed is 8, 2 to the half is radical 2 plus 1. So there it is, 4/15, 9 radical 3 minus 8 radical 2 plus 1. Okay, I'm done, folks. In fact, I'm done so early, I'm going to tell you where we're headed when we come back from spring break. Okay. Just so prepare you for that. If we can get ahead, we might as well. So what's happening after that is we're doing triple integrals. And again, they can get really, really long. So I can just tell ahead of time, this is going to be minimum 15.6. When we come back on April the 6th, I guess it is. I'll show you a little bit of that. But let me do the focusing thing over here again for question 8. Right, so we had 6 homework problems and I did 4 of them. And over here, we had 4 homework problems and I did 3 of them. Okay, so if you just bear with me a little longer, I'll give you the quiz and we're going to get out real early. So just where we headed. Okay, so triple integrals integrate over a 3-dimensional object, delta x, delta y, delta z. Okay, so see number 1 there on page 1029. X is between A and B, Y is between C and D, Z is between, they call it R and S. Okay, in general, notice they have a cross, which doesn't mean cross product. X is between 2 numbers, Y is between 2 numbers, Z is between 2 numbers. Okay, so your Riemann sum would have a sum of 3 things, right? Because you have a delta X, a delta Y, and a delta Z, which in general is delta V, right? So we are going to have triple integrals. Triple integral of f of x, y, z, dv. What is dv? Okay, well, here's Fubini's theorem. You can put this on the next cheat sheet, but I really don't think you need it. Page 1030. Okay, so here's a function, dx, dy, dz in some order. If these are all constants, in this case they are, x goes from A to B, y goes from C to D, z goes from R to S. Here they got dx, dy, dz. That's actually not our favorite. Our favorite's going to be dz, dy, dx in general, because we usually have z as a function of x and y. And then next we usually have y as a function of x. So our favorite, so-called, is dz first, then dy, dx. It doesn't say so here, but let me just write it as dz, dy, dx is so-called favorite. Okay. But there's actually 6 orders that you can have it in. So here's another change. They put dy, dz, dx. Okay. There's 6 ways you can list these. Some of you know that in combinatorics, that's 3 factorial, 3 times 2 times 1, because you say, how many choices do you have for this first letter? You have 3 choices, either x, y, or z. Okay, once that's done, how many choices do you have for the next one? 2. Right, and then that leaves only 1. So 3 choices times 2 choices times 1, or 3 factorial. Okay, if we were to go to 4 dimensions like time, x, y, z, and t, you would have 4 factorial, which is 24. Okay, so you have dz, dy, dx, and dt in some order. Then you would have 4 choices for the first letter, and then 3 choices for the next, and then 2 for the next, then 1 for the next. So you have 24 possibilities if you were to go to 4 dimensions. Don't worry, we're not doing any of those. Okay, so, I mean, this is bad enough. Okay, so that's Fubini's theorem. Okay, and notice, just like in 2 dimension, it works inside out. So you do x first, then y, then z when it's listed like that. So this inside one is for x, this inside one is for y, this one is for z. So notice if they do dy, dz, dx to get the same integral, y comes first. So y went from c to d. And then if they put z next, z originally was going from, what did they say, R to S. So that comes second. And then finally, x goes from A to B. And you have so many other possibilities that are there too. Okay. So that's what's happening there. Okay, that's the nicest case when all you have are constants. Okay, for x you have constant, for y a constant, for z you have a constant, which means the region you're integrating over looks like a box. Okay, see that box there? They got an example, and they chop it up into so many pieces: delta x, delta y, and delta z, right? So if all these boxes, I'm not going to call them cubes. They don't have to be cubes. I guess the way they drew it is like a cube, but one of these slices doesn't have to be a cube. There's a change in x coming out at you, a change in y left to right, and a change in z up and down, right? But you can have any region. You could integrate over a sphere or an ellipsoid or whatever. Then it looks like, let's see, the most general one would be 7. Yeah, 7 is our so-called favorite, dz, dy, dx. I don't think you have to put that in your cheat sheet, but look at the way it goes. On the inside is z. Okay, I can't show it to you, but see that first integral symbol next to the f of x, y, z? It says u1 of x and y. Okay, that means z can have a function of x and y. Then the one in the middle, dy, is a function only of x, but the outside is only the constant. So that's consistent with what we said before. Remember when we're doing double integrals, right? We did double integrals. Double integrals. Let's say you had a dy. This one can be a function of x, but the outside could only be constants. So this is the higher dimensional analogy. So if I have dz on the inside, this is allowed to have x and y, function of x and y. Okay. Then by the time you get to y, it can only have a function of x. And by the time you get to the outside, you must have constants. Okay, so that's the way it works in general. Okay, so number 7 in general. See that inside one that goes u1 of xy, u2 of xy, that inside one can have a function of the other 2 letters. Okay. This is our favorite, but if it says dx, dz, dy, if dx is first, then you're allowed to have y and z in this expression. Okay, then when you get to here, okay, so if you have dy and the outside is x, you can have a function of x here and here, or they can be constants, but again, the outside one is only allowed to be constants. So there we go. That's where we're headed. Okay, so just a simple, yeah, and well, you don't have to put this in your cheat sheet because I already talked about it, but on page 1034, volume is a triple integral dv. So if you ever want to find the volume, it could be a triple integral of dv or 1 dv. And right now, dv has 6 forms, right? dz, dy, dx, or any other permutation of those that we said, right? But there's actually going to be more than that. Okay, so an example of what I'm talking about, 15.6. Okay. So, yeah, look at number 4. I know it's not a sign, but see how it goes, 6xy dz, dx, dy, right? The first one is dz. So the inside integral is allowed to have x and y, and you see it does. It goes from 0 to x plus y. Question 4. Then next it says dx. If dx is next, then it can have a function of y. And you see the middle one, it goes from y to 2y. That's allowed. But then the outside y, dy, has to be constant, 0 to 1. So that's consistent all throughout, notice. Okay. For example, see number 8. Number 8, it says dz from 0 to 2 minus x squared minus y squared. So that inside integral is dz. It's allowed to have x and y. And then dy, well, dy only goes from 0 to 1. That's okay, that's allowed. But it's allowed to be a function of x. But the outside one must be constants, 0 to 1, as you see there. Okay, and then later on, they write it like that. Then you have to figure out which one is on the outside and which one's on the inside and so forth, right? Right, so that's leading up to what we're doing on the Tuesday after we come back from break. I got time, it's only a little bit past 7, so sorry to keep you longer, but this would just help us later. You're gonna get out real early. So Yeah, number 9. Just take a look. It says x goes from 0 to 3, y goes from 0 to x, z goes from x minus y to x plus y. Okay, based on what we said, can you tell which one must be on the inside, which one must be in the middle, and which one must be in the outside? Right? Z has to be first because I see it has 2 letters in it, right? Z goes from x minus y to x plus y. So the inside integral is z and dz. Which one must be next? Y. No choice because it says y goes from 0 to x. So the middle integral would be integral from 0 to x dy, and then dx is last as x goes from 0 to 3. Okay, so that's where we're headed for 15.6, triple integrals. All right, so I'm done, folks. So does anybody have any question? If not, we'll go to the quiz, and that's it. Then have a good spring break. I'll see you on Tuesday, April the whatever. I can find it here. Tuesday, April the 6th. Okay, any questions, please? Wait just a moment. All right, quiz time. And even doing this quiz would not be that hard. Okay, so get your cell phones ready or be ready to do a screenshot. Here you go. Use polar coordinates to determine a double integral over the region D of square root of x squared plus y squared dA. D is the semicircular region bounded by y equals radical 16 minus x squared on -4, 4. Okay, so figure out this region, obviously. Figure out what the region represents. So that'll tell you R goes from blah, blah, blah to blah, blah, blah. Theta goes from blah, blah, blah to blah, blah, blah. Oh, they already give you the hint. It's a semicircular region. Okay, make the substitutions, and there you go. Okay, so I'll hold it here just for another few seconds, and then go ahead and get started. I'll set up your breakout rooms. As usual, put your first and last name and first and last name of everybody else in your group. As soon as you get it right and everybody else in your group has it right, you can disappear, send me the quiz, and then have a good break. Okay, I will assume everybody now has it. Okay, so I'm going to make this disappear. Go ahead and get started. I'll stop the share. I'm going to stop the recording also.